All right, so yeah, this is the session on competitions. We put out this call for competitions that it would be affiliated with the first AutoML conference. We got 4 submissions and we iterated with all of them, and actually in the end accepted them all because they all had nice properties and covered different areas, different sub areas of AutoML. And well, so the idea is that we're going to have a competition program every year. We'll also, we had 2 different types of competitions. We had the competition where that would start right away. And we had one that was a launchpad competition. Nobody used that option. So in the future, we might want to think about how we can, I think it's hard to say it's now a launchpad and you get a talk next to AutoML. It's a whole year. I think that's why nobody did go for it. But we will have a call much earlier this time. Last time it was sort of a relatively late decision to have competitions. And but competitions are really a driver for the field. And because of that, I'm thrilled that there were 4 competitions. There will be posters for each of the competitions afterwards, and also for some of the winners of the competition. So the winners had the option to put a poster. Not everybody did, but there's also some posters from the winners. And then, without further ado, I would pass over to Nathan for the first.
Thank you very much. The challenge I will introduce today is meta-learning from learning curves, lesson learned from the first and second round. So it's joint work with Isabelle Guyon, Li-Shen Sung, and the lead author of the work, which is Man Nguyen, who really did like most of the hard work for organizing this challenge. And I would also like to thank our sponsor, who really did make this challenge possible. So without further ado, so the motivation behind this challenge is a desire of recycling knowledge. So if we have learned already to perform well on several tasks, we would like to learn quickly to act on a new task. And so this enable to alleviate most of the training of ML models, which become to be quite an issue right now with like the larger and larger models that we see every day. And it's a very active area of research, which involve meta-learning, few-shot learning, transfer learning. And so to be a little bit more precise, we would like to especially capitalize on meta-learning, to use past experience to be able to train model faster with fewer examples. Probably there is some conversion issue, but basically we have all this hope to fewer example and better performance. And the output of this training process, so it's not actually a trained model, but a meta-trained learner, which means that it's a learner that you can use on a new task and supposedly will learn very quickly to perform well on this new task. And so the first round winners of this first round. And so meta-learner needs to solve 2 problems. So you have the algorithm selection. So which algorithm should you choose next? And the budget allocation. Which budget should you allocate to training this new algorithm? And so the idea here is to use the information contained on the learning curve to come up with a good strategy. And it's really a trade-off between exploration and exploitation. So if you are in this setting, you have already uncovered some learning points of several algorithms. So you can either try to exploit what you have revealed, which will be here, for example, choosing the blue algorithm, which is the most promising algorithm, and train it for longer. Or you could try to explore. So, for example, choose a new algorithm, like the gray algorithm, which has been hardly trained, but has bad performance. And so hopefully, maybe it will be better than the other one. So you have this dilemma, which is a classic in reinforcement learning and this kind of frameworks. And so we have organized a first round, which has finished a few months ago, but is still accessible in this website. So it's still kind of a benchmark if you want to use that. And the setting is as follows. So we had 30 data sets from a wide range of tasks, regression tasks, classification tasks, several sizes, from a couple hundred of data points to a couple thousands of data points, and 20 algorithms. So it was a random forest, boosting methods with various hyperparameters. So it's really like an algorithm kind of recommendation problem where you have to choose from a discrete set of algorithms. And so 25 of these data sets were given to the learner to meta-train, and 5 were used for testing. And one important thing is that we had to pre-compute every learning curves for each dataset algorithm pair. So at the end, it's quite computatively intensive, and it allowed basically participants not to have to compute that by themselves. It's given by the environment. So as you probably noticed, the challenge is designed as a reinforcement learning technique. And more precisely, the setting is as follows. So you have an environment which give observation to the learner. So the observations are like the revealed learning curves for the algorithms that were chosen by the agents, and meta features about the dataset itself. And given this observation, the agent can choose which new algorithm to try and which budget to allocate to the training of this algorithm. And you have this iterative process where the agent will reveal more and more points on the curves, and we use this to compute a score. And so the score is based on the score on the test set. And so we compute the same kind of curves on the test set, and at the end, choosing at each time point the best algorithm revealed by the agent, we can construct a curve, and we use the area under this curve to compute the final score. So it can be used as a reward, for example, if you're in a remote learning setting. And it balances the exploration, so being good at the very beginning and very good at the very end. So the results are as follows. So here are represented our baselines and the top 5 teams. So we use the various kind of baseline, simple random search, which perform very poorly, average rank, which consists simply in taking the best algorithm on the meta-training dataset. There is a Bayesian optimization baseline, which is freeze-though. Best ensemble, which is simply you train every algorithm on each dataset for every short period of time, and then you only continue training the best one. And the best baseline we had was a double DQN, which performed actually very well, and was only beaten by the 3 top participants. So it's the team Moria, Neptune, and Alpert. And the first 2 actually didn't use reinforcement learning at all, but more like heuristics, clever heuristics with models to predict the performance or the time at which the next points will be available. And so there were some limitations with these settings, namely that because we had to pre-compute the learning curves, the data points we had were discrete, and there was no interpolation between those points. So for example, if you choose a budget which was in between 2 points, you will get the performance of the first one, but you had to spend the budget, so the extra budget, and which was wasted basically. So it was kind of tricky for the participants to deal with this setting. And so for this, we organize the second round, which alleviate this kind of problem. And the idea is very similar, but instead of training according to time budget, we train according to a function of the training data size. So here, basically, the action of the algorithm is to choose an algorithm and to choose a fraction of the whole data set to train this algorithm on. And it's discrete action. So the fraction can be 0, 0.1, 0.2, etc. So here is an example of this learning curve that we can get on one algorithm. And we have slightly larger, a larger set of algorithms. We use 40 algorithms here, boosting methods, KNN, MLP, etc., with various hyperparameters, and the same type of data set from the first round. And so to summarize a bit the changes, we use the fraction of the training data size. We give a little bit more information to the agent, the training learning curve, as well as the validation learning curve. The split is bigger, so we have a bigger meta test data set for each side. And the competition has finished, but you can still use that as a benchmark also on Codalab. So here's a link. And to summarize a bit the results we get here. So again, the RL baseline is very promising and was actually beaten by only the winning team in this challenge, which was the first place, and which uses a very clever, so no RL, but a very clever algorithm to and an uncrafted rule to compute which fraction of the dataset you should use to train the next algorithm and to optimize the budget allocation. And so the kind of the takeaways of this challenge are actually almost the same in the two settings. So first, framing this challenge as a reinforcement learning problem help to use out-of-the-shelf existing RL methods, which perform very well as baseline for this challenge. The second rule is that actually you have to allocate the budget jointly with choosing the algorithm you want to train on. And this is a very important thing, and that all the winning team use this kind of approach. And thirdly, which is a bit in contradiction with the first point, uncrafted switching rules have actually a lot of potential still, because the winners in every cases were actually uncrafted heuristics. And it's especially the case because we use a small metadata set, which means that it's maybe a little hard for reinforcement learning approach to learn from these few metadata sets. And so if you want to know more about that, you can go to the website where these findings and this challenge are summarized, so accessible with this QR code. So thank you very much.
Is there any question for this competition? If not, maybe we'll take questions after all the competitions. Kevin would be up next. Can you move to the next? Thank you. So this one was a competition on multi-objective optimization for transformers.
All right. Thank you. All right, so I'm Kevin. This is joint work with my student Shen Zhang. Now, first of all, as a local here, I want to say welcome. Welcome to Hopkins, welcome to Baltimore. I hope you're having some time to enjoy the city. These are some of my favorite things to do around here. If you want any tips, feel free to talk to me later. Yeah. The boat, yes, definitely, the boat is good. All right, I can't go this one. All right, so now to the technical part. So I'm from the NLP community, and I'm interested in training transformers. Transformers are everywhere now in our community. It's using machine translation, summarization, question answering. And now with these pre-trained language models, you can do fine tuning and prompting. So they're basically everywhere now. Every application uses transformers or some version of it. Now, one issue though is researchers like me, we're so busy doing our NLP questions that we don't really have time to tune our hyperparameters. So when you look at a paper in NLP, you often find that people use the default values. And we know this is not optimal, right? So for example, say I train a MT system, machine translation system for German to English. I know I would do better if I run AutoML when I try to apply it to a different data set like Swahili English, right? So I remember yesterday at the panel, there's talks about sort of 5-year goal for AutoML or what's the holy grail, right? And of course, getting the next GPT-4 would be great. But I also really resonate with one thing that they mentioned actually is it would be nice if AutoML is just part of the tool chain for practitioners. And I think it's really insight, like practitioners like me would really appreciate having this. Okay, so now going to the competition. I keep going to this slide. So AutoML is great. We can run it for transformers in our area, but currently I haven't found a good sort of multi-objective solution. And this is something that really is a pain point for us practitioners. I think the figure isn't showing here well. So here I'm plotting 700 different transformers I've trained for a Swahili to English task. And there's a bunch of points here that you can't see for some reason. But basically, we want things on the Pareto curve. We want things that are very high quality translations. So blue score is a measure of that. And we also want things that's very fast at decoding time. So we want things on the Pareto frontier, but it's actually really hard to think through how to find models that are on the Pareto frontier. So just as an example why this is hard, these are the hyperparameters that we often tune for if we have the time to do it. And this is actually the same set of hyperparameters we have in the competition. So for example, architectural parameters, number of layers, number of hidden layers in the feed-forward unit, your word embedding size, number of attention heads. All these hyperparameters we know if we increase it, it usually gives us better accuracy. It also slows down our system, right? So that's the trade-off there. There's also pre-processing hyperparameters. I think maybe people outside the field might not know this as well, but this is essential. So when the sentence comes in, we often have to divide up the words into subword units, right? So for example, say the word transformer is a word. Now the word transformers, is that a different word or should that actually be transformer plus S, right? So if you think about parsimony in models, you want to divide up words in a way that makes sense. So when we divide up into very small subwords, we can usually have a very small softmax layer that will speed up the model. But at the same time, it also means our sequences become longer and transformers are sort of n squared according to sequence length. So then it becomes slower, right? So then here's a hyperparameter where we can't even think through a priori, how it relates to speed and accuracy. And also learning rate, that's something that affects our final performance. So we also put that in. Okay. Yeah, so basically all of these are hyperparameters that ideally we want to tune for, but we just don't have the time to do that. So, so that's why we put out this task. Like we're kind of hoping that some of you will help us solve this problem. So the way we set up this task is this straightforward HPO task. A set of hyperparameters is encoded as some kind of vector X, and it goes into training. And after you train it, you measure its accuracy, you measure its speed, and then you have a loop. And you're trying to basically find the X that maximizes f of X with as few function evaluations as possible. All right, so this is standard setup. Here we'll have two metrics we care about. We care about accuracy. So this is how good the translation is, for example, and then we care about inference speed. So how fast, how many sentences can you process per second? Okay. All right, and then we'll measure things, basically how many, given the fixed budget, that's our evaluation criteria, given the fixed budget, say you can train 200 models, how many Pareto points do you find? Okay. And one thing with doing this turns out to be very difficult is that it takes us a long time to train models. So for a standard data set that we use in machine translation, it probably takes a week on the GPU to train just one model, right? So of course, we don't want the participants to be doing this. So we basically spend a lot of money trying to build this ourselves and build a tabular data set. So that's what we have now is we have a big tabular data set. The nice thing now is anyone in this community can use this data set. You don't need to know anything about the NLP domain. It's just a table with hyperparameters and then the accuracy and the speed. Okay. So just a few more details about this data set. So we made sure we have different machine translation data sets. So for example, we have one data set focusing on Chinese to English translation. This is from the TED Talks domain. So the TED Talks actually, that's a popular data set for our field now because there's many people are interested in TED Talks and people are interested in translating them. Also, we have a Russian English also in TED Talks. Also Japanese English and English to Japanese, we tried both directions. This is general web data. This is very large data set. So this is the one that took us a week to train each model. And then we also have some smaller data sets. These are low resource, what we call low resource languages, African languages where currently vendors out there don't offer good translation services for these languages. So we really want to improve the technology there. So we have a few models there. And then finally, there is a blind test set. It's cut off over here, but it's a Tagalog, a language of the Philippines. And that's sort of similar characteristics to this. So basically, all this data is online. You can use it freely, however you want. And the task is, I give you these 6 data sets. You can do any kind of HPO algorithm you want, and then you'll be evaluated on the blind test set. Okay. Okay. And just to sort of give you a flavor that this is a sort of interesting data set, here we're measuring how different the different data sets are. So basically, for example, we look at Russian to English. We take all the best transformer models and rate them. And then we look at, say, Chinese English and see how does that ranking change. So we're measuring the Spearman correlation here, and you see that it's quite varied. There are some that are pretty high. For example, English to Japanese and Japanese to English is 0.9. That's pretty high. That means you can probably transfer the hyperparameters. But then there are some that are very low. So if you have a Japanese English system, you want to use it for Swahili English, you probably need to run AutoML again to get a good result. Okay. All right, so that's sort of set up. We give you a bunch of data sets, you try it, and then you test on the new data set, and we see who gets the most number of Pareto optimal points. And here are the results. So the top team goes to AutoML at Freiburg. So this is a very interesting method, TPE with transfer learning. Shuhei will have a poster later, so definitely do go by. These results are surprisingly good. I feel like almost you solved my problem for me. The second place went to Merkabat Lofty from ESI Algiers. They did some kind of mix of having XGB rank and also the genetic algorithms. And as you see here, we're measuring number of Pareto points discovered, and we're also measuring the standard deviation because we can run multiple times. Okay, so I think that's basically what I wanted to say. Very interested in HPO on transformers. Multi-objective is super important. If you're interested, try out our tabular benchmarks. And we're planning to build more benchmarks. Now with this experience, I realize I can have you solve my problem for me. So we're gonna build new benchmarks. And if you have any suggestions on what makes sense, I'm really happy to hear about. Okay, thank you very much.
Any question right now?
Thank you very much for this very interesting benchmark and competition. I wanted to ask about the metric, as you're saying, the number of discovered Pareto points. If they're all very cluttered at one region, then it would be very bad, actually, right? So we would like to cover the entire Pareto front, right? So would you change that in the future, or what do you think about that?
So for this evaluation metric here, we just wanted to be simple because we were putting on Coda Lab. We didn't know if people were experts or not. So that's why we just say, okay, number of Pareto points. But yet, like you said, ideally, we want the full Pareto frontier. So if there's a metric that can measure that, maybe that would make more sense for the next round. Yeah, definitely.
Yeah.
Great work, and I've always been a proponent of people coming up with more transformer benchmarks. One question though is just probably I missed a detail. In the set of hyperparameters, most of them were, I think, architectural hyperparameters. Is the training procedure held constant, or the training procedure, does it vary? Like learning rate, optimizer?
Yeah, okay. So what we did was, most were architectural hyperparameters. We only had one initial learning rate hyperparameter for Adam, and we actually fixed the learning rate scheduler. So from our experience with machine translation, there's one scheduler that works very well. We basically keep things constant, keep learning rate constant until you start to saturate, and then you drop it. So that's what we do. But yeah, there are different learning rate schedulers, but we just wanted to make it simple. So just one initial learning rate, and then we fix the scheduler. Yeah.
Great. I think we'll go to the third competition.
Thank you.
This one is on dynamic algorithm configuration, and I'll let you talk about what that is.
Hi. Good afternoon, everyone. So today Aditya and Caroline, we're going to be speaking about the competition on DAC for AutoML that we sort of organized during this whole time period. So let me just try to go to the next slide. Yeah. This was a competition which was a collaboration between our teams at Hanover and Freiburg, where the people that you see have sort of worked on DAC and developed the whole field. So let me give a bit of an intuition on how that works. So we all know that, the standard way is to have some static hyperparameters for a model and sort of train it to the end for that. And we have all been asking, I guess, since we are at the AutoMLConf', the question, then can we do better than this? And one of the ways is to, for example, do something like a schedule that is heuristically driven or something like that. But in dynamic algorithm configuration, we essentially ask the question that can we dynamically tune certain set of hyperparameters using a learnable policy that can do that over the time period of learning. So you have an agent, you have a certain time step, and you want a controller to sort of do the tuning for the agent and learn to do it based on certain conditions. The way we formalize this is using contextual Markov decision processes. Since the controller is being controlled, usually we would expect using reinforcement learning or something like that. So you have an algorithm, you have a controller that applies an action, which is a set of hyperparameters, could be a single hyperparameter, could be multiple, and you get a reward for that. And this whole formulation is contextualized by different hyperparameters as they are set during the learning. So you set a frequency, say 200 steps, set the hyperparameter, set it again, and your controller wants to learn a policy that can do that. So the two things that we want to check are, can we beat a static baseline and can we beat a heuristically driven schedule? And how do we do that? The way we set up the competition was to have two variants of this problem. One was the supervised learning case, and the other was the reinforcement learning case. So DAC for SGD and DAC for RL. In the SGD, what we did was we allowed the participants to control the learning rate for the AdamW for neural nets on a vision benchmark. And for the reinforcement learning case, we instead, in addition to having parameters, we also allowed the participants to actually set the algorithm and change it out of the set of the three algorithms that have been mentioned here. And the prizes were a monetary prize offered by our sponsors and a certificate, of course, and the AutoML book signed by the original authors. Let me hand it over to Caroline to explain the SGD track.
Hey, so So what we want to do now is translate our problem of interest into our CMDP or MDP. And our first track is DAG for SGD, so DAG for supervised learning. So we are interested in tuning the learning rate of Adam W, and we want to solve or we want to make training neural networks on small scale image data sets better. And of course, we want to have different tasks, and different tasks comprise different data sets, different model sizes, and also varying training parameters. And we hope to find a policy or a solution combining the task and maybe the state, for example, the validation loss, so the partial learning curve, into something that gives us an appropriate learning rate. And as a cost metric, we use the test loss of the per epoch checkpoint. And it wouldn't be a great challenge if we wouldn't have anything to compare against. So we have baselines, of course, a constant learning rate, we have cosine annealing, we have reduced learning rate on plateau, and a simple reactive scheduler. And we evaluated everything by computing the average rank across 400 test instances or 400 learning tasks. And of course, for the test, we evaluate on unknown seeds and unknown tasks, but we stay in distribution. So let's take a look at the winners or at the results, so to say. So we have 23 total participants, from which we have 4 eligible results or submissions. And the first place is Machi, the second Wu Nguyen, and then we have a baseline, TAC, and NPU-CHY, and we can see the score. But what's more interesting is to look at a specific test instance, for example, like this, and we can see how the different learning rate schedulers look like. So let's look at Machi. He has a reactive scheduler, looking at the validation loss and adjusting the learning rate accordingly. And we have Wu Nguyen, which uses a reflectional sigmoidal shape, and also TAC with a similar shape. And as a reference, of course, cosine annealing. And what we can see from that is that even simple sigmoidal shapes perform better than baselines. And also, of course, reactive schedulers are very promising. And I think we can do even better than that. So that's all about this track. And Aditya will present the reinforcement learning track. So here you go.
So now coming to the reinforcement learning problem. So here, as I mentioned before, we had 3 target algorithms, which are pretty standard for most of classic control stuff in reinforcement learning. So DDPG, PPO, and stack. And we used the stable baselines 3 implementation of that. Interestingly, to create a standardized kind of variation that we could test upon, what we did was we used the formalism of contextual MDPs, but for classic control environments using our benchmark Carl. So if we imagine a simple control task, it is governed by certain differential equations. And in a standard setting, the agent has to, for example, learn how to balance a pendulum. Now, what's not changing in any standard reinforcement learning setting is probably the mass of the pendulum, the length, or the angle, all these parameters that are being shown here. So in our benchmark in Carl, we allow a user to change them in a principal manner so that now we can create distributions of these pendulums with different lengths, different masses, different angles. And we can also create sets of training and testing distributions. So now you train an agent on these training distributions that are given to the participants. We can test how their policies perform dynamically on a held out testing set of contexts in these environments. And this is what we did for that. And in our setup, there were essentially sets of 3,000 inner loop steps, which is you take any algorithm here mentioned, run it for 3,000 steps, and then change something. Maybe change it to a different algorithm with different parameters, change the parameters of the same algorithm, however they want to do that. And in total, this could be done 10 times. And in our solution space, essentially, as I mentioned, the dynamic algorithm configuration policy would essentially be these 10 different changes that are applied onto these things in the whole process of training. And the metric, as I mentioned before, would now be essentially given 5 different environments and 5 held up values of these changing contexts. We just do that for the same number of seeds across 4 different participants and see how their policies perform during the test set. And finally, to get the rank of the participants, we would get the area under the curve metric of the rewards over 100 episodes in the testing set. In our competition, there were 13 participants, out of which there were finally 2 eligible submissions. And the baselines that we provided to them were, as I mentioned before, a sanity check baseline, which is the zoo hyperparameters in the stable baselines 3 implementation of PPO, and a heuristically driven sort of a replacement for that using PV2. So it's an offline schedule. It's not changing. It's fixed. It's trained offline. So you basically just compare it against a schedule that's not dynamic. And what we found was that the winning entry sort of combined these 2 baselines that we had provided. So it took a set of the zoo hyperparameters and the schedule. And in addition to that, tuned the base learning rates to get to beat our dynamic baseline. In addition to that, the second place tuned just the base learning rate. And as sort of what we found was, so the sanity check baseline is sort of beaten by just tuning the base learning rate, but it cannot beat the schedule that has sort of been found by PV2. And to beat that, actually, as I mentioned before, you have to sort of combine them together and get something more dynamic running out there. And this is what we observed in our competition. What we found from this was another thing that we sort of expected while putting the choice of these different algorithms, that when you change the algorithm, you get more differences as compared to changing the hyperparameters because you're sort of going to a different part of the space altogether. In addition to that, by design, we had these environments have held out changing dynamics in the testing time. So even with most of the dynamic stuff that was being done, we did observe some overfitting on the training set. And finally, we saw that offline tune schedule for PV2 for these environments did not work as well as we would expected that to work, given that the environments were changing. And so it was a legit test to see how these can perform. And let me hand over to Caroline back again.
Let me conclude this and let me share our insights. So they are pretty simple. We can do better than static configurations, and we can also do better than heuristic-driven schedules. But of course, I think, as you also notice, there is loads of room to improve, and we would like to work further on that. And feel free to check out our poster later on the poster session. Then we can tell you about specific methods, and also one participant also provided some information about their submission. And speaking of the participants, I would like to give now the certificate to Woon Yen, which is here, I guess. Would you come to the front? And I would like to hand over the certificate. So thanks for your solution and for participating. We have the certificate for you, and we will ship the AutoML book and the monetary prize, of course, also.
Thanks a lot.
Thank you. Thank you for your attention, and have fun with the next talk.
Any questions? All right, maybe at the end. The fourth and final talk here is actually going to begin online. It's about a, yeah. So it's Rea Suktanker. Sorry. Yeah, so this is a zero-cost NAS competition. It was organized jointly by my team and various other collaborators, including Dibadipta Day, who will man the poster. But Rea knows all the details, so she will talk about it. Unfortunately, none of the organizers from my team could come due to visa issues, COVID issues, other disease, sickness. So yeah, but we have Rea here, so I'm very happy to have her give this talk.
Thank you. Am I audible?
Yep.
Okay, okay. Hello, everyone. I'm going to present the competition Zero Cost NAS, which we organized at the AutoML conference. This was a joint effort between the Freiburg AutoML lab and our collaborators from University of Oxford and Microsoft Research. So to start with, what is a zero cost proxy? So neutral architecture search provides us with an automated way to search for optimal architectures. But many of these popular techniques are still quite expensive. And this problem even worsens when we move to larger search spaces, which are time consuming to train and which are massive in terms of having to search over the macro and micro architectures. So zero-cost proxies, on the other hand, use negligible amount of computational resources to obtain a quick estimate of the performance of network architectures. So the computation time for such proxies is often the matter of a single forward or backward pass. And for example, some simple proxies could be the number of parameters, the flops, and there are some others like SynFlow, Grasp, SNP, whose formulas you can see here, and I would refer you to the zero-cost proxies for lightweight NAS paper by Abdel Fateh for further details. So the second motivation is, like, recently we have seen a lot of surge in the research on zero-cost proxies, but the fundamental question which remains is how useful are they and how robust are they across different search spaces? And the iClear blog post by White et al. Was what motivated us to have this competition in the first place. And we have another recent submission from our group, which studies this at scale, the NAS Bensuit Zero. And this is the figure from that paper, wherein you can see that there's not a single winner in zero-cost proxy which wins across different search spaces. So now to give you an overview of the competition, we were given different architectures from different benchmarks in NASLib, which is the NAS research library we maintain in our group. The participants develop a zero-cost proxy to maximize the rank correlation between the proxy scores and the actual architecture ranks. The submission is then scored with the average Kendall-Tau correlation across a set of NAS benchmarks. The submissions are run with a fixed hard CPU limit. And this is because we want to keep the spirit of zero cost alive. So roughly to define how the development procedure in the competition would work is that you have these benchmarks from NASLib and you develop a proxy on them. And then during the development phase, you have a signal on how well these proxies would probably generalize, and dependent on that, you improve your zero-cost proxy. And finally, you rank the proxies dependent on an unseen test set. So the phases of the competition were first that the participants developed their own zero-cost proxy based on the wide range of publicly available benchmarks we have in NASLib. And then they push their submission to the leaderboard to get an estimate of how well the proxies perform on a held out set. And then finally, they submit their proxy and we score it on an unseen test set. This is the Coda Lab page for the competition and our competition website. So the benchmarks we used the large variety of benchmarks from NASLib. And there were some specific ones that benchmarks that we created for this competition, like TransNAS Bench Micro with Nina Pro dataset, those are the data sets from NAS Bench 360 and so on. And one thing to note here is that we made sure that the data sets during the development phase and the test phase were quite different to reinforce the goal of the proxies being generalizable across benchmarks. So now coming to the evaluation criteria, we use the Kendall-Tau correlation coefficient to score our submissions. The proxies should be different from the ones available in NASLib. We already have quite a lot of proxies implemented in NASLib, and we had a constraint that the submitted proxies should be different. The proxies should not be designed for specific benchmark data sets present in the evaluation set. And this was because essentially a submission that does this would break for the test phase because we have very different benchmarks for the test phase. And this is also a way of rewarding the zero cost predictor that generalizes the best. And we capped the time limit to 80 minutes on 32 GB CPUs. Now coming to the results, the winning teams for the competition were Team Codex, Team Warwick, and Team DGCN at the first, second, and third places. The first and second teams used a normalized version of the SynFlow and Fisher zero-cost proxies. The third team used a product of two proxies, that's the grad norm proxy and the number of parameters proxy to score the architecture. I would recommend you to check out their posters for further details. So now to conclude the main discussion and the takeaways from the competition. What we see is that the most zero-cost proxies do not generalize well when moving across different benchmarks and data sets. There are some proxies which work for only specific types of benchmarks and specific types of search spaces. So combining these proxies appropriately and effectively is still challenging. Possible interesting directions that we should look forward to as like a community would be to study the similarities between search spaces based on the proxy scores. And we could potentially also look into using zero-cost proxies to accelerate the existing NAS methods. Thank you for your attention, and let me know if you have any questions.
Any questions?
Hi, great competition. I'm wondering, has anyone tried to use the winning submission to improve a NAS method, or is that planned for the future?
Not yet, but like I know of people in our lab who are working on using zero-cost proxies for NAS, and definitely using one of the competition submissions would be an interesting idea to incorporate that.
Thank you.
All right, any further questions for this competition? Not the case. Any questions that you thought of by now about any of the competitions? All right, it's also not the case. One thing that I would like to summarize from all the competitions, also as Kevin said very clearly, well, this is a way to get the community solve your problems. The competitions that we organize were academic competitions where we try to push the state of the art in one very specific research field. But Kevin already had something for like real world transformers. And I think one thing that would be really nice in the future is if some companies could actually have some data where they say, well, this here is, if you help me solve this, then this actually really has a business impact for me if you come up with a method that can solve these problems. And so this is just a big encouragement to anyone in industry who has data. You have a lot of brilliant people who would work on your stuff basically for free. We had very few prizes here. I think one competition had like $1,000 and the others did not have anything. If there's some real world data and there would be a prize of $10,000, $15,000, the community would be all over it. So, and PhD students need topics, and if there is a competition with a monetary prize, then that is direct motivation for the student that there is actually someone who cares about this. The money is also nice, but it just shows that there is direct impact if you solve this problem. And that is a big motivator for the students. And the students, they just need to publish. They publish on something. And if they get excited about your problem, then yeah, good for you. And they work for free. So should be motivation for you to think about that. With that, I would like to close the session. And we're going back to posters. And we will meet here again for the keynote and panel with Timnit Gibru at 5 p.m. All right, see you then.